Thermodynamics is the branch of physics that studies the relationship between heat, work, temperature, and energy, and how energy is transferred and transformed. It is a macroscopic science that uses the 4 laws of thermodynamics to explain how energy changes in a system and whether that system can perform useful work. Thermodynamics applies to various topics in science and engineering, especially physical chemistry, biochemistry, chemical engineering, and mechanical engineering, complex fields such as meteorology. Key concepts include the system and surroundings, different types of systems, open, closed, and isolated, and how thermal energy relates to the motion of particles. Key concepts: energy, heat, and work. Thermodynamics explores how heat and work are different forms of energy transfer, and how they relate to a system's temperature and other physical properties. System and surroundings. A system is the specific part of the universe being studied, and the surroundings are everything else. Energy can be transferred between the system and its surroundings. Types of systems. Isolated system. A system that cannot transfer matter or energy with its surroundings. Closed system. A system that can transfer energy, as heat or work, but not matter. Open system. A system that can transfer both matter and energy. Macroscopic versus microscopic. Thermodynamics is a macroscopic science, meaning it describes the bulk properties of a system without regard to the molecular motion within it. Statistical mechanics, in contrast, takes a microscopic approach by using the probabilities of molecular states to explain thermodynamic behavior. The laws of thermodynamics. The behavior of thermodynamic systems is governed by a set of laws. Zeroth law of thermodynamics. If 2 systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. This law establishes the concept of temperature. This law was formulated by Ralph H. Fowler in the 1930s, long after the first, second, and third laws were established. For an example, imagine a thermometer placed in a cup of hot water. After some time, they reach thermal equilibrium, for example 100 degrees Celsius. If you then place the same thermometer into a second cup of hot water, and it reads 100 degrees Celsius, the zeroth law tells us that cup A and cup B are at the same temperature, even if they aren't touching. First law of thermodynamics. Energy cannot be created or destroyed, only converted from one form to another, or transferred, or energy can be transferred between physical systems as heat, as work, and with a transfer of matter. This is essentially a statement of energy conservation. Second law of thermodynamics defines the existence of a quantity called entropy, which describes the direction, thermodynamically, that a system can evolve, and quantifies the state of order of a system, and which can be used to quantify the useful work that can be extracted from the system. This law explains why certain processes happen spontaneously and others do not, and it leads to the idea that heat cannot spontaneously flow from a colder body to a hotter body. Common statements of the law is increase of entropy. The entropy of the universe, system plus surroundings, always increases for any spontaneous process. Heat flow. Heat spontaneously flows from a hotter body to a colder body, not the other way around. Energy quality. Energy has quality as well as quantity. Some energy is always degraded to a less useful form, waste heat. During conversions, limiting efficiency. Kelvin-Planck statement. It's impossible to convert all heat from a single source into work in a cyclic process. Example, no 100% efficient heat engine can be possible. Implications. Arrow of time. Entropy's constant increase defines the direction of time. Refrigeration. Air conditioners and refrigerators work by expending energy, work, to force heat from a cold space to a warmer one, defying its natural flow. Heat death of the universe. Eventually, all energy might spread out, leading to maximum entropy and no more useful work, though this is trillions of years away. In essence, the second law explains why things fall apart, energy disperses, and why we need constant energy input to maintain order in our lives and machines. Third law of thermodynamics. The entropy of a perfect crystal at absolute 0 Kelvin is 0. Or, this thermodynamics law states that as a system approach absolute 0 temperature, absolute 0 Kelvin is the lowest possible temperature where all classical motion stops. Its entropy approaches a minimum, constant value, which for a perfect crystal is 0, signifying perfect order. Essentially, it means perfect crystals at absolute 0 have only one possible arrangement, ground state, making them perfectly ordered. And it's impossible to reach absolute 0 in a finite number of steps. And it's impossible to reach absolute 0 in a finite number of steps. Applications and importance. Cryogenics. Essential for designing cooling systems and studying materials at extremely low temperatures, leading to phenomena like superconductivity. Absolute entropy calculation allows scientists to determine the absolute entropy of substances, providing a baseline for thermodynamic calculations.